So the first speaker is Ishii Yamazaki from Sandia National Labs, good friend and colleague, and we've been working together on this paper in particular, and look forward to hearing Ishii's presentation. Thanks.
Okay, so thank you, Steve. So this is a joint work with Mark Hoemmen, Eric Bowman, and James Elliott from Sandia National Lab, and also with Steve Thomas and Kasia from National Renewable Energies. Okay, so this talk is going to be about Krylov solvers, which is, as you know, it's a very popular method for solving large-scale linear system applications and used in many applications. And these include these DOEs and ECP applications. That's been the main focus of our applications for the last few years. And I'm going to be showing some results with one of the ECP applications that we've been working on called ExaWind. And these solvers are based on two main computational kernels. So the first one is SPMBs, or sparse matrix vector multiplies, and they are used for generating this Krylov subspace. And it's typically combined with some types of the preconditioners to improve the convergence rate of the solvers. And the other one is orthogonalization kernels for generating orthonormal basis vectors for this subspace. And this is going to be the focus of this talk. So these kernels require some communications. So SPMBs typically require some point-to-point or neighboring communications. And depending on the preconditioners, but these preconditioners typically requires some types of communications. But at least for this talk, we're going to treat this SPMB and preconditioner as a black box provided by the user. So we won't be touching these SPMB or preconditioners, but we're going to be mainly focusing on orthogonalization kernels. Okay. So these orthogonalizations requires this global or reduce among all the processes. And each of the process is going to be using either BRAS1 or BRAS2 kernels, which is typically memory bound. So this orthogonalization can become quite expensive on the current computers. If the SPMB and preconditioners scale better, these could become quite significant in the iteration times. Okay. So there have been quite a few techniques developed to address these communication issues. So for example, S-step Krylov aim to avoid some of the communications by generating a set of S vector at a time. And this gives us potential to reduce some of the communications by factor of S. And we also have this pipeline variant of the solvers, which try to hide some of the communications by overlapping or pipelining these Krylov iterations. So simply hiding these communications will give us maximum speed up of tools. But if we manage to pipeline these iterations effectively, we may be able to obtain even higher performance speed ups. So we have already implemented this S-step and pipeline GMRES and CGs in Trilinos. And since these are based on Trilinos stack, it can run on either CPUs or GPUs on the distributed system. So just to give you some ideas on the performance of this solver, I want to show some performance results we got with the collaboration with one of the ECP application called ExaWind. And they are trying to simulate this flow dynamics of wind turbine plants. And this experiment is done on Intel Haswell node at NASC Corey computers. Okay. So this is first result, shows strong scalabilities for solving pressure system. And this is done using algebraic multi-grid preconditioners in Mulus of the Trilinos, which I think next Jonathan's going to talk about next. And at least using the input tech given by Steve, this GMRES required around 100 iterations to converge. And for the CA-GMRES, we generated this Newton basis to maintain this stability of the solvers. And using this setup, both standard and S-step GMRES converged in about same number of iteration count. Okay. And by avoiding these communications, we get a speed up of about 1.4 to 1.3. So for the pipeline GMRES, so we use pipeline GMRES for solving momentum system. And for this system, we use this symmetric Gauss-Seidel preconditioners, and it converges in about 5 to 20 iterations. So initially, this pipeline GMRES took a longer time to solve the system. And this is because in order to pipeline these iterations, they need some extra computations. But as we push the number of process count, we start to see some benefit of hiding these communications. Right? So we've been looking at if we can further improve the performance of these solvers. So for example, in S-step, we have at least 2 global or reduce still for orthogonalizing this set of S vectors. And if we need to re-orthogonalize, the number of or reduce is going to basically doubles. And also for the pipeline GMRES, we currently only have this single reduce classical Gram-Schmidt, which may lead to some unstable behavior of the solvers due to the loss of orthogonalities. So we've been looking to integrate this single reduce Gram-Schmidt into our solvers. So this technique has been already talked about in a couple of other talks. So we had another talk by Cassius, I think on Wednesdays, which is in context of GMRES and MinRES. And there's another talk tomorrow using this for the eigensolvers. But really the main difference here is we're going to be using this for this S-step and pipeline Krylovs. Okay. So I'm going to be mainly focusing on this S-step GMRES. So the first thing we did was to combine these 2 synchronizations, one needed for this classical Gram-Schmidt to orthogonalize this set of S vectors against previously orthonormalized vectors, and the other one needed for Cholesky QR to orthogonalize these new vectors against among themselves. And this is the same technique used in pipeline GMRES to combine these two, but here we are just extending it to orthogonalize S vector at the same time. So in the beginning, we have this big dot product here, these ones. Then after that, we're going to have this classical Gram-Schmidt to orthogonalize this vector against the previous ones. And we can basically simply update this Gram matrix and use that to do this Cholesky QR. Right? And by doing this, we can reduce the number of global or reduce to 1s for every S iterations. But if we need to do this re-orthogonalizations, we're going to still have 2 synchronization points for every S step. Okay. So, but fortunately, we can actually unroll this CGS2 or doing CGS twice recurrence. So here we have this standard recurrence to apply CGS twice to this set of new vectors. But if we expand this, we get this new equation here, where this T matrix is just this Gram matrix for this previously orthonormalized vectors. So in exact arithmetics, this becomes identity. So this matrix here in the parenthesis is simply identity matrix. So this becomes just applying classical Gram-Schmidt once. But in final questions, this becomes not identities. So we are basically updating this R matrix using this T matrix. Using this, we can basically apply this classical Gram-Schmidt twice using this update matrix R. And nice thing about here is both of this R and T matrix can be computed with just one global reduce. And by using this, we can basically apply this CGS2 with just a single global reduce. Right. So another way to improve this stability is to replace this CGS with a modified Gram-Schmidt, which is more stable. But standard algorithm for modified Gram-Schmidt will require at least J-1 synchronizations to orthogonalize against J-1 vectors. But again, we can unroll this MGS recurrence to obtain this formula here. So now we have this small triangular solve that we need to apply to update this R matrix. But doing this, we can again apply this modified Gram-Schmidt with just a single global reduce. Okay. So finally, in order to really maintain the orthogonalities, we may have to apply this Cholesky QR twice. And we're going to do this by delaying this second Cholesky QR until the next step to orthogonalize the next set of vectors. And by doing this, we can basically combine the global reduce needed for the second round of Cholesky QR with the next round of CGS, or modified Gram-Schmidt. And interesting thing here is this Gram matrix, which is needed for Cholesky QR, is actually the same matrix T, which is used for this single reduce CGS2 and MGS. So in terms of the computational cost, there really not much overhead for computing this Gram matrix. After this Cholesky QR is applied, we can just simply update these matrices T and R's and move on to the next set of vectors. Right? And by doing all of this, we can apply this either CGS2 or MGS combined with Cholesky QR with just a single global reduce. Okay. So just to summarize, so this is just complexity of this new single reduce version of Gram-Schmidt. So for example, for CGS, we can have just one single reduce without no difference in the flop count. But for modified Gram-Schmidt, we have a slight increase in computational cost. And this is because we have to compute this new matrix T. And for the CGS2s, we actually have fewer flop counts. And this is because some of the big matrix operation is now merged into ones. So here are some of the numerical experiment that we did. Yeah. So here's I have a CGS2 and MGS CGS1s using different orthogonalization schemes. So this green one here is just a standard GMRES. And these three are the S-step using a standard orthogonalization where I'm just orthogonalizing one vector at a time. And this is the standard S-step using block orthogonalizations, but it requires multiple global or reduce. And this is the last one is this new single reduce versions of the orthogonalizations. And the main thing here is just all of these single reduce versions obtain the same orthogonality errors as the standard schemes. And we also tried with different matrices. So this is 3D Laplace problems And now I'm increasing this step size to 5s. And basically, we are getting about same orthogonality errors using also different orthogonalization schemes. So in terms of performance, so this is performance experiment we did on the summit using GPUs. So this is for the 3D Laplace, and I didn't use any preconditioners for this test, so it's because like when I was running this experiment, I wasn't quite sure how good this preconditioner will run on GPUs, but now I think also preconditioner are running quite well, and I think Jonathan's going to talk some about multi-grid, so I should definitely try with preconditioners. But at least for this case, so for example, this black lines is standard GMRES, and this blue is S-step using the traditional block orthogonalizations with multiple global reduce, and this red one uses this new single reduce versions of orthogonalizations. And one thing I should mention is that performance of this orthogonalization kernel really depends on the performance of underlying brass kernels. So for example, if we look at this modified Gram-Schmidt, actually this S-step is running much slower than this standard GMRES. And this is because the Kubras version of GEM that I use wasn't quite optimized for this tall, skinny type of the shape. But as you increase this number of GPUs, you start to see this benefit of avoiding some of the communications here. We clearly see this single reduced versions has much nicer scalabilities, even for this classical Gram-Schmidt versions. Okay. So we also integrated this new scheme into pipeline GMRES. So this is one of the stress testing in terms of numerical stabilities. And this pink line shows the convergence of standard GMRES. And it goes all the way to maximum ratio norm that we can get for this particular matrix. On the other hand, this pipeline, the original pipeline GMRES actually failed about like 50 iterations. Okay? And by using this new CGS2 and modified Gram-Schmidt, we can push this down to over here. And we couldn't quite catch up to standard GMRES, and we are working to further improve the stabilities of this pipeline GMRES. Okay. So in terms of the performance, so we wanted to see if this new synchronous Gram-Schmidt has any performance penalties. But so this is on the CPUs, and it's just showing these new types of one synchronous modified Gram-Schmidt doesn't have much performance penalties while improving the scalability, the performance, stability of the solvers. Okay, I think that's it. So just to summarize, so we now have this communication avoiding and pipeline version of GMRES and CG in Trilinos, and it's available through this Veros software package. And we've been testing its performance and stabilities with applications, including this ExaWind applications. And we've been trying to improve its performance. And we integrated this single reduce version of orthogonalization schemes. And we are running more tests, performance tests, especially with preconditioners. And I think we need to do more numerical studies to really understand the effect of these new orthogonalization schemes.
Please thank our speaker.